Okay, so again, plan for today is 12.5 equations of lines and planes, and supplement to be posted tomorrow on 12.6 cylinders and quadratic surfaces. And that'll wrap up the chapter 12 material and the material for this first week. So remember, 12.1 through 12.4 is kind of review material that's typically covered at the end of Calc 2. You might have even gotten to this material at the end of Calc 2, so this might be a bit of a review for some of you, or you might not have gotten to this yet. Okay, so equations of lines and planes, in particular in three-dimensional space or higher dimensional space. So we know that a line in 2D space is determined by, say, point and slope, or what we might think of more generally as location and direction. And in the three-dimensional space, we have a similar idea that a line in 3D space is determined by two properties, its location and direction. By location, we mean a point on the line. So a certain three-dimensional point, a point in 3D space, that lets us kind of anchor that line at that point. And direction, what do we mean by direction? Obviously, something as simple as just a basic slope isn't going to work so well here. But in this case, we can say, well, we know that direction or that vectors have as one of its characteristics a direction. So we can say we want to have a line that's in the direction parallel to a specified vector. So our location, a point that's going to be on the line, just kind of like in 2D space, but direction here we're talking about being parallel to a given vector. A little kind of side note, you might think, well, wait, isn't a vector and a line, aren't they kind of basically the same thing? They're somewhat similar, but there's a bit of a distinction here. A vector has two properties, magnitude and direction. So it has a length and a direction, but it's really not localized to a particular point in space. So one of the kind of magical characteristics in a sense of a vector is you can move vectors around and it's still the same vector as long as it has the same magnitude and direction. If it moves in space, it's still the same vector. Whereas a line has a fixed location, but in a manner of speaking, it has an infinite magnitude. It kind of goes in its direction as far off one way or the other way as it can go. So where a line has a fixed location, but in some sense an infinite magnitude, or it doesn't have a sensible magnitude, a vector has a fixed magnitude, but it doesn't really have a fixed location, so to speak. Okay, so let's think a little bit about a line in three-dimensional space. So I'm going to draw a little picture here. I think drawing these pictures live is helpful. Whenever I get to more complicated pictures, I might draw them beforehand so they can look a little prettier, but a lot of times if I can draw them live for you, it's a little easier for you to kind of track what's going on than to have everything there all at once. So we'll start with our three axes. Z, Y, and X like this. So our three-dimensional coordinate system. Hopefully this is familiar at this point from the 12.1 through 12.4 material. And say we have a line in three-dimensional space here. Let me give it a little bit more of a slope than that, so it doesn't just look like the y-axis. So we have a line here. And on this line, we have a point, let's call it P, an arbitrary point, P, X, Y, Z. So this is a three-dimensional coordinate, but that's constrained to be on this line, this point P. I can think of there being a vector going from the origin to point P, and maybe I'll call that vector R bar. And I know that R bar, this correspondence between the point of the three-dimensional coordinate of the terminal point of a vector when its initial point is at the origin, and the components of the vector, I know that R bar can be represented as X, Y, Z in component form. I might also have another point on this line. Maybe this point, I'll call it P naught, X naught, Y naught, z naught. And I have a different vector. I'll kind of point to it so it's not quite as cluttered. And I'll call that r bar naught. So this is vector r naught, r sub 0. And again, that vector is the one where if we put its initial point at the origin, its terminal point will be at p naught at the coordinate x naught, y naught, z naught. So we say the coordinates of r bar naught are x naught, y naught, z naught. Or I'm sorry, the components of r bar naught are x naught, y naught, z naught. Now I see that I can think of another vector, say the vector going from the coordinate p naught, the point p naught, to the point p, this vector here. This red vector, again, I'm going to kind of point to it from over here, just so things are a little less cluttered. I'm just going to call it A. So A is the vector from P naught to P, and it is vector in the direction of the line. I might also think that I have a vector maybe that we'll call V, a vector V that is parallel to vector A. And we know that that means that, we know that that means that V times some constant T will give me A. So now suppose that I'm given for the location property, basically this vector r bar 0, or really this point p naught. And suppose that I'm given vector v for the direction that I want my line to go in. So I've now been given location and direction. How can I put these pieces of information together to get an arbitrary point on my line? Well, I see that really what I'm doing is I'm taking the vector r bar naught, adding to it the vector a bar. So I see that r bar, the blue vector here with my terminal point at xyz, an arbitrary point on the line. What's that going to be? That's going to be r bar naught plus, well, we could say vector a bar, but again, vector a bar is going to be different depending on what point we're talking about. So we could be a little more general and say that this is going to be t times v bar times a direction vector. So here, if t was 0, we'd just be talking about the point p naught being the terminal point of this r bar vector. If t was whatever number it needs to be, so that tv bar equals a, then we'd be looking at, say, this point here on the line. If t gets larger positive, it's just going to keep going further to the right on that line. Or if t gets negative, then it's going to cover the left side of that line, right and left, as we are looking at them here. So t can be any real number from minus infinity to infinity, and t parameterizes this line. As t increases from negative infinity up to infinity, this point traverses along this line. In the case of how we have it drawn here, it would traverse it from more or less left to right. So this is our vector equation for the line, and it has a parameter t, a real number that's involved. Okay, so that's kind of the geometry. Hopefully that gives a little bit of intuitive sense to what we're going to say next. Again, the vector equation for the line is r bar equals r bar naught plus t times v bar. Note that when I write vectors by hand, I usually put a bar on top, but written in the book and in my notes, typically vectors are going to be indicated by a bold variable, just because bold is hard to get across in writing. I write the little bar on top to indicate what's a vector, and then the scalars like t here don't have a vector bar on top. So again, the vector equation is r bar plus tv bar. Again, r bar is our vector whose terminal point is at a specific point on the line when its initial point is at the origin. V bar is a vector parallel to the line, so r bar naught gives the location information, v bar gives the direction information, and we have a parameter that is a scalar t, just a single real number t, from minus infinity to infinity. If we say that r bar naught is x naught, y naught, z naught, and that v has components a, b, c, then we can say that the coordinates of the line, the coordinates of the points on a line, x, y, z, are as follows. So we have these parametric equations for x, y, and z. X equals x naught plus, if I can select it here, plus a times t, right? This is just coming from the first components matching up on the left and the right side here. On the left side, r, its first component is x. On the right side, r naught's first component is x naught. V's first component is a, so x naught plus a times t. And then likewise for y and for z as well. We have these three equations, one for x, one for y, one for z. They are coupled by this parameter t. They all have the common parameter t in them, but they have different, direction vector components, different location vector components. So the parametric equations of the line with the parameter t involved are these three equations. But you might remember from Calc 2 that when we have parametric equations, sometimes it's helpful to eliminate the parameter. And if we do that here, we can solve each of these three equations for t. And we can see in the first equation, we would have t equals x minus x naught over a. And similarly for the other two, provided that a, b, and c are non-zero. Then we end up with what are called the symmetric equations of a line, because if we solve each of these three equations for t, then clearly we have t equals one thing, t equals a second thing, t equals a third thing. Those three things must themselves be equal. If a, b, or c, if one of them is zero, then it's easy enough to see that, for instance, if a is zero, then we just get x equals x naught, and then equality between the y and the z information. So if one of them is zero, then we can go back to kind of first principles and see how that would affect these symmetric equations. Okay, so any questions to this point? And you can always feel free to either pop a question in chat or raise your hand, or if I'm not seeing something in chat, I usually have my chat window up, but if I just don't see it for some reason, you can, unmute yourself when there's a pause and ask any questions you have. Okay, so moving on then, what if we are interested in a line segment? What if we're interested in a portion of a line? Say I'm interested in some chunk of a line. I don't want the whole line though. In particular, what if I'm interested in a line segment from one point to another, or from one terminal point of a vector to another terminal point of a vector? So the equation of a line segment from R0 to R1 is, well, we just take t times r1 plus 1 minus t times r naught, and let t vary from 0 to 1. What are we doing here? Well, when t is 0, r bar of 0 is, well, we have 0 times r1, and we have 1 times r naught. So when t is 0, we're just starting at r naught. When t is 1, well, now we have 1 minus 1 or 0 r naught plus 1 r1. It's just r1. So we're traversing this line segment from r naught to r1 using this parameter t from 0 to 1. Okay, let's look at a couple examples. Oh, that every once in a while, OneNote doesn't work so nicely with formatting. I was trying to get these to center, and every time that I would center them, like 15 seconds later, they would just automatically realign to left align. I don't know why. But like 95% of the time, OneNote's great, but sometimes it has little quirks about it. Okay, so example 1, let's try to find a vector equation for the line passing through the point 1, 2, 3, and parallel to the vector 2, -1, -4. So we have direction information parallel to the vector 2, -1, -4, and we have location information that we need to go through the point 1, 2, 3. And then once we find that equation of the line, we want to answer this question. For each of these 3 points, is the point on the line or is it not on the line? Okay, so what is our set of equations here? Well, we see that we have r bar equals r bar naught plus tv bar, or we can use our parametric equations to write it out more explicitly. But I see that r bar is going to be, well, it's going to be x naught plus at for the first component, or it's going to be 1 plus 2t. And I try to make my t's have like a kind of a curly tail at the bottom so they don't look like pluses. But if you're ever confused what's a t and what's a plus, especially on this little trackpad, it can be sometimes a little bit hard to tell the difference. But 1 plus 2t for the first component. And then for the second component, we have the second coordinate of the point plus t times the second component of the direction vector. So that's what, 2 plus -1t or 2 minus t for the second component of our bar. And then for the third component, 3 plus and -4t or 3 minus 4t. So every point on the line can be written this way for some choice of t. Maybe it's t equals 10 gives me this point, and t equals -20 gives me that other point. And vice versa, for any choice of t that I plug in here, t equals 100 or 0 or whatever, that will be a point on that line. So a point is on the line if and only if it looks like this for some t. So we could kind of look at this in one way. We could say, well, and by the way, this is the answer to the first bit. So for part B, I suppose, we could look at, say, 3, 1, -1. We want to know whether this is on the line. If it is on the line, then the x, y, and z components all have to match up, right? So if it is on the line, then for my x component to work out properly, I need to have that 3 equals 1 plus 2t for whatever choice of t we end up being stuck with. And this tells me that t has to be 1. For the x component to work out properly, t must be 1. Now I can check the other two. For the y component to work out, well, if t is 1, do the y components work out? 2 minus t, or 2 minus 1, is that equal to the given y component of 1? Yes, it is. The y component looks like it's working okay. What about the z component? Right? These have to all work out for the same choice of t. We can't just have 3 different choices of t. It's got to be the same choice of t. So we check that the x's work out for t equals 1, and that's why we plug t equals 1 in here. Again, doing the same thing for z. Well, for z to work out, that means that 3 minus 4t, or well, we know that we're only concerned with t equals 1 here because that's the constraint to make the x coordinate work out. So this is 3 minus 4 times 1. Is that equal to the proposed z coordinate, -1? And we see that works as well. So for t equals 1, we do get this coordinate. So yes, this coordinate is on the line. And in fact, we discovered something extra here. We saw that it's on this line for the choice t equals 1.
Wouldn't it fail because it's -1 times -4?
So this is -4 times t, but t is actually +1.
My bad.
Yeah, so up here for the x constraint, 3 equals 1 plus 2t. So that tells me that t has to be +1. And so you are correct. If up here, if we had gotten t equals -1, 3 minus 4 times -1 would give me 3 plus 4, or 7, which would not be -1. That would be a point that's not on the line, but that wasn't what we ended up getting. But yeah, so since we have t equals +1, when we do 3 minus 4t with t equals +1, we get 3 minus 4, which is indeed -1, the proposed z value. Yeah. Now, one thing that we can see here is that this is a little bit tedious to do, right? We have to really deal with this parameter directly. We have to solve for it and then plug it in. If we could use the symmetric equations, maybe that would be a little bit easier. So maybe I'll copy these down. For the second point here, let's try to use the symmetric equations. So what are the symmetric equations for this line? Well, I have x minus x naught over a. Remember, this is up here. This is x naught, y naught, z naught. And my direction vector is a, b, c. So here I have x minus x naught, or x minus 1 over a, which is 2, must be equal to y minus y naught, or 2, y minus 2 over b, or -1. And that must be equal to z minus z naught, or z minus 3 over c, -4. Right? So if I say make a choice for x, that turns this into just a number, and that constrains what y and z can be from these other expressions. And likewise, if I made a choice for y, that would constrain x and z. If I made a choice for z, that would constrain x and y. That's what I would expect from a one-dimensional structure, right? A one-dimensional line, if I kind of set any distance in any way, then that kind of constrains everything else. That tells me exactly where I'm at on that line. Okay, so I could investigate the 0.1/2 9/4 4, in light of these symmetric equations, I can just plug in x equals 1/2, y equals 9/4, z equals 4, and see, do those three expressions turn out to be numbers that are equal to one another? Why did I set the x portion of r bar equal to 3? Here, is that the one you're talking about? This
Yeah.
3 here.
Yeah.
Okay. Yeah, so that's because we were investigating the line, or I'm sorry, the point on the line 3, 1, -1. We were asking, is this point that somewhere in 3D space, is it on this line? So on one hand, so if it is, on one hand, the x coordinate has got to be 3 because that's the point that we're interested in. On the other hand, the x coordinate has got to be 1 plus 2t for some value of t because that's another representation of all of the points on this line. And then we just say, okay, well, 3 equals 1 plus 2t. My x coordinates match for what value of t for t equals 1. And then I check that against, oh, I don't know how I did that. I check that against the y coordinate up here. This y coordinate of 1 is where the 1 from here came in. And I check that against the z coordinate, of -1. So for these y's and z's, for the x, I see that the only way for the x coordinate to match up properly is if t equals 1. When t equals 1, what are my y and z coordinates on this line? And do they match up with the y and z coordinates that are proposed from this point that we're asking whether it's on the line? If they do match up for that same t, then yes, that point 3, 1, -1 is on the line. And if any of them don't match up, then that point is not on the line.
Okay. Thank you.
Yep. Yes, we could solve for t with x, y, or z. So I could have chosen to solve 3 minus 4t equals -1. I still would have gotten t equals 1. And then I could have checked the x and y, or I could have solved, what would it be? 2 minus t equals 1. I'd have gotten t equals 1. And then I could have checked x and z. Yep. So I could have started with any of the three to nail down my t number, and then evaluated the other two with that same parameter t, with that value of the parameter t, to see if they matched up. Yep, we could have started with any of them. I just chose x because it was the first one, but you certainly could have started with y or z. Yep. Okay, but for the second point, 1/2 9/4 4, we could do it this way. We could also use the symmetric equations. And we could have used the symmetric equations for the first 0.31 -1 as well. If you want a little bit of practice, you could do 3, 1, -1 with the symmetric equations, and 1/2 9/4 4 using the parameter, although the parameter might be a little messy for this one. But here for the symmetric equations, the question is, does this set of equalities hold for this set of choices for x, y, and z? If 1/2 9/4 4, when plugged in for x, y, and z into the symmetric equations, gives me three expressions that result in three numbers that are all the same number, then yes, this point is on the line. If it gives me any two numbers that are different, then this point is not on the line. Or in other words, I want to know is 1/2 minus 1 over 2, is that equal to 9/4 minus 2 over minus 1, and is that equal to 4 minus 3 over -4? Well, 1/2 minus 1 is -1/2 over 2 is, I think, -1/4. Is that equal to the second expression? 9/4 minus 2, that's 9/4 minus 8/4, or 1/4 over -1 is 1/4. Looking good so far. And is that equal to 4 minus 3 is 1 over -4, -1/4. So yes, they all, when I plug in this choice for x, y, and z, all of my three expressions in the symmetric equations end up being -1/4. So this is a point on the line. And then let's look at the last example here, 2, 0, 1, and see, is this a point on the line? So maybe I'll just kind of do that off to the side here. Is 2, 0, 1 a point on the line? And again, we could ask a question like, okay, 1 plus 2t equals 2 for what value of t, and then plug that value of t in for y and z. We could do it this way. We could also do it with the symmetric equations. Either way, symmetric equations just save us the hassle of having to find the parameter t and then plug in. But here we're asking, is it true that 2 minus 1 over 2 equals 0 minus 2 over -1 equals 1 minus 3 over -4? 2 minus 1 is 1 over 2 is 1/2. Is that equal to -2 or -1, which is 2? And is that equal to 1 minus 3 is -2 over -4 is 1/2? Well, the x and the z are equal, but neither of them is equal to the y. So because, for instance, this equality does not hold and that equality does not hold, the x and the z expressions happen to be equal, but they don't match the y. So no, this point is not on the line, because our symmetric equations do not hold. They aren't equal to one another when we plug in 2, 0, 1. So a couple follow-up questions. We have a couple representations for our line. We have the vector representation, or I suppose the parametric representation, which is pretty similar to the vector representation, or the symmetric equations. Or for this particular problem, I have this vector equation and these symmetric equations. Are these unique? Is it true that for this line, this entity that exists in three-dimensional space, that this is the only way to describe such a line? Any thoughts on that? Is this unique or not? As a hint, I mean, we found a different point on the line, or even a third point on the line. Any thoughts on whether this is unique? Is this R bar here, or these three symmetric equations, are they the only ways to describe this line? Or is there maybe a second or a whole bunch of vector equations that could describe the same line, or a whole bunch of sets of symmetric equations that could describe the same line? Well, yeah, this is not going to be unique, because I mean, I could have just as well chosen my location point to be 3, 1, -1, and the direction vector to be the same vector, right? I would arrive in a sense at 3, 1, -1 for a different value of t, but I would have had something like R bar equals what, 3 plus 2t minus plus 1, 1 minus t, and minus 1 minus 4t, had I used 3, 1, -1 as my location point, and this vector 2, 1, 2, -1, -4 as my direction vector. So these are not unique. I could kind of choose any point along the line to be my location point, my coordinate that I'm using to fix the location. That'll give me the same line, Now I'll arrive at a specific point for different values of the parameter t when I choose different kind of initial points or different location points. I'll arrive at a given point for a different value of the parameter t, but still, as t goes from -infinity to infinity, it'll still trace out the exact same line. It'll still be the same full set of points, whether I choose, this point or that point or this point or some other point on the line to be my kind of location point. So no, these are not unique. There are many ways to write a line, or to write the same line, the equations for the same line. Would we get a different answer to the second part, to whether these three are on that line if we used a different representation? I think I pretty much answered that no. We would get, if we went with the kind of solve for t approach, we would get a different value of t. So for instance, over here, for 3, 1, -1, we'd get t equals 0 instead of t equals 1. But we would still get consistency or inconsistency. We'd either get t equals 0 for all three x, y, or z, or inconsistency that it wouldn't quite work out for some of them for whatever points. Our ABC values the distance. It's not they're not giving the distance. These are giving the direction vector. Yep. So our direction vector v is ABC. Yeah, that vector v does have a magnitude, but the magnitude is really unimportant here because that vector v always comes into play with a parameter t. So we're always scaling it up or down as needed. So we could even use a different vector, which is something that I'll ask later on, somewhere down here. I kind of alluded to this question, but we can address it now, that if I had used a different vector here, parallel to the vector 2, -1, -4, if I had instead asked parallel to the vector 4, -2, -8, that would also give me the same line. Again, I would arrive at a specific point for a different value of the parameter t, but it would still be the same line. It would still be the same set of all points. Even if we had a different vector, a different direction vector, as long as it was in the same direction. If we changed its magnitude, it doesn't really matter. So another follow-up question in 2D, in 2 dimensions, it makes sense to ask for the equation of a line through a given point, like we asked here, but instead of parallel to another line, saying perpendicular to another line. Right, that would be a reasonable, well-defined question to ask in 2 dimensions. Find the line through this point and perpendicular to this other line that's given. Well, with a similar question in 3D, find a line perpendicular to a given vector through a given point, would that be similarly well-defined here? And I think, well, any thoughts on that? I think the answer helps lead us into some of the thought processes along that are involved in planes. But the answer is, well, not really. Right? Why is that? Well, if I have a line in 2D space, say this line, the line perpendicular to it has a specific slope, right? It has a given slope. But in 3D space, if I have some direction vector, there's a whole bunch of vectors that are perpendicular to this, right? There might be one kind of pointing in the direction of the x-axis. There might be one pointing kind of this way, or one pointing kind of back into the screen a little bit. There's lots of vectors with very different directions, not just the plus or minus or 180 degree kind of thing, but very different directions that can all be perpendicular to a given vector. So if I say I want you to be parallel to this red vector, that sets a direction. But if I would say I want you to be perpendicular, well, there's lots of different directions, lots of different vectors that you could choose that would be perpendicular to this one. So that doesn't quite give us enough information to figure out what the line is, or to figure out what direction vector we ought to use in such a problem. So in 2D, saying I want a line that goes through this point that's perpendicular to this other line makes sense. In 3D, doesn't make so much sense. But we actually might see something interesting from here, that kind of the set of all vectors that are perpendicular to a given direction vector actually kind of all lie in a plane, in a two-dimensional structure. That's going to be important coming up here. Okay, example 2. Let's try to find a vector equation for the line passing through these 2 points. So I have location information given. I have 2 points that are on the line, so I actually have more than enough location information given, but I don't have direction information directly given. But I do know that for these 2 points, I'm just going to draw them kind of schematically, not being careful about which octant they're in or anything like that. But I have 2 points here. I want the line passing through these 2 points. I have location information for that line. It's kind of anchored at these 2 points. What is my direction information? Well, it's actually not too bad. My direction information is just the vector going from one point to the other. So I first have to find my direction information v bar, and that's just the vector going from one point to the other. Or I'll take this point minus this one, or so it'll be the first component is 1 minus -2, the second component 3 minus 1, the third component 5 minus 0. Or my direction vector v bar that my line has to be parallel to is going to have components, well, 1 plus 2 is 3, comma 2, comma 5. So this is my direction information. What should I use for my location information? Either point. I could pick either point. It doesn't matter. I'm going to go with, for location, I'm going to go with the point -2, comma 1, comma 0. So I could rephrase this as I'm looking for a line passing through this point, -2, 1, 0, and parallel to this direction vector. So the location information is given by the point -2, 1, 0. The direction information is given by being parallel to v bar 3, 2, 5. Again, could you have used this point to get your location information? Absolutely. That would have given a slightly different looking equation for the line, but it would be the same one. It would be the same collection of all points in three-dimensional space. Yeah. But here we have r equals r naught plus TV, or get a little more space here. Our first component, -2 plus t times 3, so plus 3t for the first component. For the second component, we have starting at 1, and then plus t times v, the second component of v, plus 2t, And for our third component of R, we have 0. I won't write that in, but we have 0 plus t times v, or t times 5t. Or for our symmetric equations, what do we have? We have x minus x naught over a, or x minus a negative 2x plus 2 over 3, comma, equals, and then y minus y naught over b, or y minus 1 over 2. We're basically just solving x equals negative 2 plus 3t, solve that for t, and then put that here and do the same for the y and the z. And then we have z minus z naught, z minus 0 over c over 5. These are our symmetric equations. Again, if you had used a different point on the line for the location information, you'd have gotten slightly different looking equations here, but they would represent the same line. If you had used a slightly different direction vector, one that's parallel to this one, maybe 6, 4, 10, or negative 3, negative 2, negative 5, again, you'd have gotten slightly different looking vector equations, symmetric equations, but they would still represent the same collection of points in three-dimensional space. The main difference would be that a certain point on the line would be associated with a different value of the parameter t. So they might look a little different, but there are lots and lots of representations of the same line, just using slightly different information, slightly different but equivalent information. All right, any questions on lines? Okay, so let's jump ahead to planes then. A plane in three-dimensional space is determined by two properties: its location, like a line, and also kind of like a line, it's, in some sense, its direction. The location, just like a line, is, we think of it as a point on the plane. Direction is a little more complicated because a plane kind of stretches out in two dimensions, so it kind of has a lot of directions. If I just told you one vector that I want to be, in a sense, lying in the plane, that doesn't quite give enough information, right? If I told you that, say, a vector along the x-axis lies in the plane, well, your plane could be kind of the plane with also the y-axis in it, or so kind of a horizontal plane, or it could be more like a vertical plane that has the x-axis and the z-axis in it, or maybe some kind of 45-degree plane that kind of cuts through the YZ, well, I guess the YZ plane, it cuts through that plane at like a 45-degree angle and has the x-axis in it. There are a lot of different planes that could have a specific vector in it and have a certain location. So for direction, we actually think back a little bit to what we set up here, that if I give you a vector, and instead of asking for something that's parallel, if I ask for something that's perpendicular, then I can imagine all of these vectors kind of pointing out perpendicularly. Really, they kind of span out a plane, a two-dimensional surface. Somebody asked, did class start early today? Nope, class starts at 6 every day, so 6 to 7:35. Yeah, so the set of vectors that are perpendicular to a certain vector, and say that go through a certain point, they span out a two-dimensional surface, a plane. So it kind of almost seems like the direction information that we should be given, if we're interested in finding a plane, we should be given a certain vector that is actually perpendicular to the plane. So if you think of, if you have a piece of paper that's, well, we'll take that to be kind of flat, and if you, put your pen in the middle of it pointing straight up, if I gave you the information about the direction that pen is pointed, that tells you what direction the plane, that piece of paper has to also be pointed. So kind of interestingly, the information that we're given for lines and planes looks pretty similar. For a line, we're given a point on the line for the location information. For a plane, we're given a point on the plane. But for the direction information, we're given a certain vector that's parallel to the line. Or for the direction information for a plane, we're given a certain vector that is perpendicular to the plane. So, so sometimes there are very similar concepts that differ only a little bit. And sometimes that can be, fairly annoying, because if everything is pretty similar except for this one little difference, that can be a little tricky. So just to remember that if you're given a vector that's perpendicular to the information that you're interested in, chances are you're looking for a plane there. And if it's given as parallel, chances are you're looking for a line. Okay, so let's draw a little figure here. We'll see how nicely I can draw this. This one's a little more complicated to draw. So here we have Z, Y, and X. And we have a plane up here. Of course, this plane goes out in all directions forever, but I'll just kind of schematically draw it as a little square up here. So there's my plane. I'm just shading it in a little bit just so that it kind of looks a little more solid. Now I can think of this plane as having some points on it. I can think of it as having, let me switch colors here, having a point on it. Let's call it P naught. X naught, Y naught, Z naught. That can be associated with a vector R bar naught, whose initial point will be at the origin and terminal point at P naught. I can think of another point on the plane. Let's call this point P, X, Y, Z. And it can be associated with a vector R bar. And then I can have a third vector pointing from P naught to P. And this vector, I'm going to kind of draw it over here. So I'll just kind of point to it. This vector will be, well, I know that R naught plus this vector has to be R. So this has to be R minus R naught. So this red vector is the difference of the two vectors, R bar minus R naught bar. Because I know that from my parallelogram law, my vector addition, R naught plus this vector has to be R. And then I just subtract the R naught over. Okay, so the other thing that I realize, and I've kind of run out of colors, I guess I'll go back to black, is that if I have a vector perpendicular to this plane, it's going to be perpendicular to R minus R naught, which lies in the plane. That's a vector in the plane. I'm going to call this vector N. And it's called N because it's a normal vector. Normal meaning perpendicular or orthogonal, normal, these all kind of mean more or less the same thing. And it's perpendicular to the plane. And really what I mean when I say it's perpendicular to the plane, I mean that for any vector lying in the plane, it's perpendicular to that vector. Or in other words, if, let's say a vector, well, I used R already, let's say a vector P is in the plane, then what do I mean? N dot P equals 0. Right? Two vectors are perpendicular if and only if their dot product is 0. Again, 12.1 through 12.4 material. So if you're not, if that's not making sense, take a look back at that review material. So if n is a normal vector perpendicular to the plane, then for any vector in the plane, the dot product of n with that vector is 0. But I know that the vector r minus r naught is in the plane. Again, because the point xyz is a point in the plane, the point x naught y naught z naught is a point in the plane. So the line segment or the vector connecting those two has to also be in the plane. All points between them must be in the plane. Therefore, my vector in red, which is r minus r naught, that's a vector in the plane. It must be perpendicular to the normal vector, because that's how the normal vector is defined. It's perpendicular to all the vectors in the plane. But these two pieces of information tell me that my normal vector dotted with r minus r naught has to be 0. Remember, r bar is just xyz. It's kind of the vector pointing to an arbitrary point in the plane. So this is my xyz. It's the bit that gives the arbitrariness of the point that I'm discussing. R naught is my location information. It's the fixed point that we know lies in the plane. And my direction information is given by this vector n that's perpendicular to the plane. So we still have location information and direction information, but we combine them together in a slightly different way because of the different information that we have to get an equation. So again, if n is a vector perpendicular to a given plane, and if r minus r naught is a vector lying in the plane, then their dot product is 0, again, by assumption of n being perpendicular. This equation can be written as, well, n dot r minus r naught. R minus r naught is just first component x minus x naught, right? X minus x naught, initial point and terminal point. Second component y minus y naught, third component z minus z naught. And here, when we have n equals abc, the perpendicular vector being abc, the dot product of these two vectors is just this. Or alternatively, we can just multiply this out. This is a scalar equation. ABC, XYZ, X naught, Y naught, Z naught are all just real numbers, and the 0 on the right, they're all just real numbers. We can just multiply all of this out, and we see we get AX plus BY plus CZ plus some constant equals 0. The constant ends up being this stuff, but we just get AX plus BY plus CZ plus constant equals 0. That really feels linear, doesn't it? We see the X, Y, and Z both come in, or all come in explicitly to the first power. So in 3 dimensions, we, in a sense, kind of have a couple of linear structures. We have straight lines and we have flat planes. Okay. Let's look at an example. Let's find an equation of the plane through this point. So here's our location information, 535. The plane contains the point 535 with normal vector 2i plus j minus k. So this is the direction information. The plane is perpendicular to 2i plus j minus k, that vector, and it goes through the point 535. Well, what did we say up here? We said that if we have a normal vector, ABC, we dot that with the with r minus r naught, which is x minus x naught, y minus y naught, z minus z naught. and set it equal to 0. So my vector n is 2, 1, -1. My R naught, or I suppose I should call it P naught, but let's say R naught equals 5, 3, 5, like that, in vector form with components. So plugging in up here, we see our equation gives us, or this information gives us our equation 2, which is A, times x minus x naught is 5, plus 1, which is B, times y minus 3, y minus y naught, and then plus -1, which is C, times z minus z naught equals 0. Or we could simplify this a bit and we get 2x plus y minus z equals, and then what do I have? 2 times -5 is -10, minus 3 is -13, plus 5 I think is, oops, -8, and that equals 0. So again, a follow-up question to think about. Well, I just said that my plane is perpendicular to 2, 1, -1. What if instead of that vector, if I had used the vector, say, pointing in exactly the opposite direction, -2, -1, +1. If I'm pointing in exactly the opposite direction, I mean, that should be the same direction information, right? Being perpendicular to a vector pointing in just the opposite direction, that should be the same plane. But these are 3 different numbers. Do we get a different line? Do we get a different representation of the line? How does that work? Or what about if we used 4, 2, -2 instead? What if we used a similar vector, same direction, but twice the magnitude? We would get different numbers. Would that be the same line? Would it not be the same line? It seems like it should, or sorry, would it be the same plane or not the same plane? Seems like it should be the same plane, but what's happening here? What about this example, 5, 4, 2, where we just took each of the components and added 3 to it? If I just add 3 to each of the components instead of multiplying each of the components by some number, would that give me the same information? Is that the same direction information or not? Well, the answer to these first two is yes. Or sorry, what did we get? This should say plane. Sorry for the typo there. Would we get a different plane? So would it be different? No. And no. We would get the same plane in each of these two cases, using a vector that's, say, in the opposite direction, or that's just twice as long. We know intuitively that should give us the same plane. What would we end up with, though, if we did say -2, -1, 1 as our direction vector, our perpendicular vector instead? Well, I'd have -2 times x minus 5, -1 times y minus 3, plus 1 times z minus 5 equals 0. But I noticed that I could just multiply both sides by -1, make a plus, and make this a minus. And then I'm just back to exactly what I had before. What if I had used 4, 2, -2 instead? What did I do here? I multiplied by -1. Well, here I just multiply by 1/2 on both sides. And again, I'm back to exactly what I started with. I see these are clearly the same one. I can multiply both sides by a constant, and that doesn't change the equation, right? If I multiply both sides by a non-zero constant, that doesn't change the equation, but it just looks a little bit different, right? It looks like I'm using a different normal vector than what I started with if I multiply both sides by -1 or by +2 or something like that. That's really all that I'm doing here when I'm multiplying my initial vector that I had used. If I use this one instead, I'm just multiplying that vector by -1, multiplying both sides of the equation by -1, or by +2 in this case. What if I add the same number to each component? What if I added basically the vector 3, 3, 3 to this? Well, 5 times x minus 5 plus 4 times x minus 3 plus 2 times z minus 5 equals 0. Well, this is not the same plane. In this case, yes, I'd get a different plane. 5, 4, 2 does not point in the same direction as 2, 1, -1. Remember, two vectors point in the same direction. Two vectors are parallel if one of them is a number times the other one. They're not parallel if one of them is the other one plus, a constant vector. So in this case, this would be a different plane. But this representation of a plane, or the representation up here before I switch the signs, they would all represent the same plane as this one up here. Again, just slightly different representations. Okay, let's find an equation of the plane through this point, 1, 2, 3, and parallel to this plane, 3x minus 2y plus 4z minus 5 equals 0. So we need location and direction information. We have location information, and it's given to us in a straightforward way. It's just R naught is 1, 2, 3. That's easy enough. Now our direction information is that we're parallel to this plane. So I'm given a plane, 3x minus 2y plus 4z minus 5 equals 0. That's a plane I'm given, and I'm told that the plane I'm interested in is parallel to that one. Well, how can I dissect the direction information I want which is a normal vector to the plane? How can I get that information from the knowledge that I'm parallel to this plane? Well, I know that this plane has a normal vector. It has to be the first component has to be the coefficient of x, right? Just look up here at this form of the equation. The first component has to be the coefficient of x, the second component of the normal vector, the coefficient of y, third component of the normal vector, the coefficient of z. This tells me what my normal vector is. I can just pull it right out of here. It's 3, -2, 4. I actually don't care about this 5 at all. That doesn't matter at all to what I'm interested in. That has to do with the location information for this particular plane, but that's not the location information for the one I'm looking for. So this is my direction information now, extracted from the knowledge that I'm parallel to this other plane, and that this plane has this normal vector. being parallel to this plane means that my plane will be perpendicular to the same normal vector that this plane is perpendicular to. I now have my location information and my direction information. And what do I want to do now? Well, now I want to use one of these two equations up here, either this one or this one, to write down my equation for the plane. And maybe I'll go with the second one because we kind of did the first one first here. So the equation for this plane that goes through this point and is parallel to the other plane is, well, ax, or the first component, or sorry, ax naught, ax, the first component of n times x, plus by minus 2y plus cz plus 4z, and then plus some constant, d equals 0. That constant is going to use this location information. I could find d using my expression up here, or I could just plug in this choice of x, y, and z, which I know is a point that has to be on the plane, and then I can solve for d. So I know that 1, 2, 3 is on the plane. So 3 times 1 minus 2 times 2 plus 4 times 3 plus d has to be 0. 1, 2, 3 is a point that is on the plane. So this equation has to hold, or I get 3 plus 12 is 15, or 11, plus d equals 0, or d equals negative 11. And I can come back up here and just say 3x minus 2y plus 4z minus 11 equals 0. So that's the equation of my plane. Again, I know that to use the equation of my plane, I need to get the normal vector. And to get the normal vector, I just look at the components of the x, y, and z terms in the given plane that I am parallel to. Okay, any questions on that?
So are there,
Oh, no, go ahead.
hi, sorry.
Yeah.
Are there different Ds per point on the plane?
Sorry, are there different what? I'm sorry, I didn't catch that.
Are there different D values for different points on the plane?
Are there different, did you say Z values?
D.
Oh, D values. Oh, yeah. Yeah, so if we had used a different point on the plane, a different R bar 0, well, so this D is fundamental to the plane. If we had used a different point on the plane, we for instance couldn't use, say, something like 1, 2, 4. We couldn't use this because we see that would give us a first 3 terms that's going to be more than 11, right? We would have, what, 15, I think, if I'm doing the arithmetic right. And then when I do that, minus 11, that's not going to be equal to 0. So the point is that to stay on the plane, so I mean, short answer is that d equals negative 11 is like a fundamental characteristic of this plane that we found. But to stay on the plane, if I wanted, say, a z value of 4 instead of 3, I could maybe drop my y value to or increase my y value to 4, I think would work. Or I could, change my z value. But the point is that this d value is going to be the same for any r naught that is on this plane. Now, if I chose another arbitrary r naught that wouldn't be on this particular plane, that would give me a different d value, and that would give me a different plane. So I don't know if that answered your question, but for any point that is on this plane that we found, it'll have the same d value. If we looked at a different point and we found that it had a different d value, that actually would be an indication that that point is not somewhere in three-dimensional space, but it's not on the plane that we're interested in here. Okay, cool. All right, any other questions on this? Yeah, that was a good question, though. This D really encapsulates this location information that we're given, which is a fundamental part of this plane. So if the D value changed, we would have a different plane. Or if this location value fundamentally changed, it could change to a different 3D point that's not on this plane. That would yield a different plane and therefore a different D value. Okay. What if I wanted to say something like, or what if I wanted to pose a question, find an equation of the plane through the point 1, 2, 3 and perpendicular to this plane? Is that a reasonable question to ask? Well, not really, right? I mean, how can we be perpendicular to another plane? There's going to be lots of kind of directions, so to speak, of plane that are perpendicular to another plane. If you think, if you hold up, say, a sheet of paper, and imagine if you could, if you were a magician, how could you could cross two sheets of paper together in a way that's kind of perpendicular. Well, I could do something like this, or I'm not going to be able to hold it, but at 45 degrees or horizontally or vertically, there are going to be lots of different directions in a sense of planes that intersect a given plane perpendicularly. So there will be lots of different choices for such a plane. It wouldn't be a well-defined answer. It wouldn't give a unique plane as the answer. Something that's an important note is there's a difference between finding a unique plane and there not being a unique representation of that plane. There are lots of different ways to describe this plane, but they all describe the same unique answer to this question, right? There are lots of different ways to describe, where was it? There are lots of different ways to describe this line, but they all describe the unique line that answers this question. So the line or the plane can be unique, even if the representation of it, the way that we describe it, might change from person to person, right? Again, we could take this equation and multiply both sides by 2, or multiply both sides by -1, and it would still be representing the same plane, just a slightly different looking representation. That would still be a unique answer to this because we're describing the same unique plane, but just with slightly different representations. But to answer a question like this, there would be lots of fundamentally different planes, fundamentally different, not just different representation of the same plane, but different planes that would answer the question if we replaced parallel with perpendicular. So it is important that that we're looking for a plane parallel to another plane. If we put perpendicular in here, we wouldn't have enough information to answer this question uniquely, with a unique answer. Okay. And then last but not least, for this one, the calculations might be a bit tedious. I think I should be able to get through them all by 7:35, but I might skip a little detail here or there if needed for time constraints. So we know that 2 points determine a line, and in three-dimensional space, it seems plausible that 3 points that are not collinear determine a plane. So let's look at an example where we try to use 3 points to determine a plane, right? We saw an example of this in lines up here, where we use 2 points. In the 3-dimensional sense, we use 2 points to determine a line. Let's try to use 3 points to determine a plane. I think intuitively this makes sense. The 3 different points that kind of form a triangle basically should determine a plane. The triangle that they form just kind of extended out in all directions, and there's your plane. So how do we actually go about doing this? Well, I know that I need 2 things. I need location information, and that's basically just given to me straight away. I could use any of these 3 points to get the location information for the plane. So I got that pretty easily. The real challenge is the direction information. I have 3 points, so I mean, pretty clearly, intuitively, we can say, okay, those 3 points, if they're not collinear, they're clearly going to define a direction that plane has to extend out, right? Those 3 points, we can think of them making a triangle. That triangle makes like a 2-dimensional surface that we can extend out. But how do I actually do that, right? When I get down to the nuts and bolts, how do I make that work? Well, I know that really what I want for direction information, I want a normal vector. I want something perpendicular to that surface. And if I think through what I've seen in chapter 12 so far, what operation gives me something that's perpendicular? Well, the cross product. So if I have 2 vectors in the plane, let me call them maybe F and G, vectors in the plane, then F cross G is perpendicular to the plane. If these are vectors that aren't parallel or right, then their cross product gives me a vector that's perpendicular to the plane. That's just what I'm looking for. If I can find 2 vectors that are in the plane that I'm interested in, I can get the direction of that plane, in a sense, the direction information, the normal vector to that plane, by taking their cross product. So I start with a high level concept. I've reduced it to something tangible, something that's a little easier to get. If I can find 2 vectors in the plane, then I'm good to go. How do I find 2 vectors in the plane? Well, if I have 3 points, let's call it R0, R1, R2, or sorry, P0, P1, and P2. I have a bad habit of just, being a little lax with my vector components versus point coordinates. There is a vector that goes from P0 to P1, and a vector that goes from P0 to P2. These are 2 vectors that are going to be in the plane that we're interested in. Okay, so let's just call P0 the first point, 1, 2, 3. Let's call P1 3, -2, 1. And let's call P2 5, 0, -4. And then we can have, let's call it R01, R subscript 01, the vector going from P0 to P1 is, so that's using these 2, its first component is 3 - 1. Its second component is -2 - 2. And its third component is 1 - 3. Or R going from 0 to 1 is 2, -4, -2. This is one vector that's in the plane that we're interested in. We have another vector that goes from point P0 to point P2. let's call that R02. I guess we could call these R1 and R2, but I'm trying to be just a little more explicit with how I label them. And again, what are the components of this vector that goes from P0 to P2? It's just basically the difference in their coordinates. So the first component, 5 minus 1, second, 0 minus 2, third, negative 4 minus 3. Or R02 is 4, negative 2, negative 7. That's a second vector that is in the plane that I'm interested in. I now have two vectors that are in the plane I'm interested in. I want to get a perpendicular vector to the plane I'm interested in. And how do I do that? Well, I can cross them. These should all have vector bars on them. If I take their cross product, that gives me a perpendicular vector. We discussed before, it doesn't much matter which perpendicular vector I have, right? Whether I use one that points a different direction or is a little bit longer, a little bit shorter, doesn't matter. As long as it's a perpendicular vector, that's all I need. And this gives me a perpendicular vector. You know, could you have crossed R02 cross R01? Sure, that would have worked. Could you have used, you know, this vector and that vector and crossed them? Sure, you know, lots of ways to do this. This cross product, since we're, I think we have time to do it. I think we can do it. I was going to say, since we're running out of time, I was going to leave it as an exercise, but we have time to run through it. So R01 is 2 minus 4 minus 2, and R02 is 4, oops, 4 minus 2 minus 7. The shortcut for computing these determinants is to copy the first two columns over. And then go down your kind of main diagonals, top left to bottom right. So we have I hat times negative 4 times negative 7, or that's times 28, plus j hat times negative 2 times 4 is negative 8. We need a little more room here. And then plus k hat times 2 times negative 2 is negative 4. And then we come down the off diagonals, the opposite ones here. These come in with a minus. And hopefully I didn't cross out so many things that I can't tell what's a negative. I don't think I did. I see my I hat comes in with a negative 2 times negative 2, which is a positive 4. But because I'm going the other way, I get a negative. So that's minus 4. My j hat comes in with a 2 times negative 7, which I had to look up above because I crossed so much stuff out. But j hat times 2 times negative 7, which is a negative 14. But again, it's going this way, so it's negative again, so plus 14. And my k hat times negative 4 times 4 is negative 16. Again, I negate it once more, positive 16, because I'm going the opposite way. So that's the shortcut for computing these determinants. Or this is the vector, first component of 24, second component of 6, third component of 12. And that does look good. So this should be negative 28. What did I do wrong here? 2, negative 4, negative 2, 4, negative 2, negative 7. Yeah, this should be negative 28. And then I think this should be a plus 4. I think this should be a +4, but I'm not seeing my arithmetic error here. This is always in my notes, I got a -24 when I did the calculations carefully, not in front of a screen, but so arithmetic error somewhere, but this is what we should have gotten for this. And then we get, for instance, we could take yeah.
I'm double checking. I'm doing the other way. So it would be a +28 minus plus a 4. Yeah, minus a 4, minus a -4. So, and I hats are always negative.
Okay. Yeah, so it should be -24 for this first component.
Yeah.
Yeah, I have some arithmetic error somewhere. That's always the risk of doing these by hand on here. But I'm not seeing it right away. So take a look back in the notes and try to fix my arithmetic error here. But in the interest of time, this is our normal vector. And again, we want to dot our normal vector with we want to dot our normal vector with a vector in the plane. That was what we mentioned way up here. Or we can think of it as just taking the components of our normal vector and multiplying them by x, y, and z. So I can have -24x plus 6y plus 12z plus some d equals 0. So that gives me the equation of the plane up to this constant. And then I take, for instance, 1, 2, 3, let's say. I know that 1, 2, 3 is a point in the plane. So -24 times 1 plus 6 times 2 plus 12 times 3 plus d equals 0. And in my notes, I ended up with d is -12. Oops. That was after I divided through by a factor of 6 up here. So d would have been -72. So we have -24x plus 6y plus 12z minus 72 is 0. And then we could just divide both sides by 6 to make things a little bit nicer. But this is a representation of the plane. Doesn't matter which of the two vectors we use. No, it doesn't. Again, we'll get slightly different representations, but it'll be of the same plane. And does the order matter? In other words, if I did R02 cross R01, that would give me +24, -6, -12. And again, that doesn't matter either because we can just multiply through by a -1. Okay, so I will stop it there.